Question 7 is a mixture of various different bits of physics. We have an object on an inclined plane, in this case a bucky on a slope. We have forces acting on this bucky, and we have work done and the work energy theorem. So there are various pieces that we're going to need to tackle in order to solve this question correctly. Let's read through the question first. We have a bucky with a mass of 2,500 kilograms. There's a constant incline of 15 degrees. That's the incline on the slope. The bucky starts from rest, and every 10 meters, the speed of the speedometer is recorded in kilometers per hour, and fortunately for you, converted into meters per second. This speed is used to calculate the kinetic energy of the bucky in kilojoules. That's quite important to note that their calculation has yielded the kinetic energy of the bucky in kilojoules, so we're going to need to convert that to joules if we need to have everything in SI units. The force is kept constant by keeping the accelerator pressed in by the same amount throughout the test drive. And here we have a diagram of the situation where every 10 meters, speed and kinetic energy of that bucky are recorded. The results are tabulated, and here we have a table of distances, speeds, and kinetic energy. The last piece of information we have is that an estimation of the friction acting on the bucky is 1,200 newtons, and that was obtained using the mass of the bucky as well as the coefficient of kinetic friction between tires and the road surface. In question 7.1, we're asked to draw a free body diagram of all forces acting on the bucky. Let's look at them one by one. Firstly, you have the gravitational force acting down. It is possible to split this gravitational force into two components. It's best to either just give the gravitational force acting straight down or to give the two components, but not both. You could have split it into a parallel component, a force parallel to the slope, as well as a force that is perpendicular to the slope. You could have done that instead of giving Fg acting downwards. You also have a frictional force acting against the motion. Remember, the bucky is going in this direction, going up the slope. So friction acts against the motion, pointing down the slope. You have an applied force acting on the bucky, going up the slope. And then you have a normal force, which is perpendicular to the slope. Remember, normal means perpendicular, so this force is perpendicular to the slope. And really, we could actually show that in the diagram as well. To get all your marks here, you basically needed to have every single force roughly to scale and correctly labeled. In question 7.2, you've been asked to plot a graph of kinetic energy against displacement. Here you would need to use the third and first columns in the table of values. The important thing is just getting everything right that you're able to get right easily. For example, the heading. A good heading should make reference to both your independent and your dependent variable. In this case, the dependent variable is the kinetic energy. Your independent variable is the displacement of the bucky. And in addition to that, it should also give you a little bit of a context or possibly a purpose for drawing the graph. So here we've spoken about the slope of constant incline for a truck, in this case actually it's a bucky, that experiences a constant applied force. So we've given a little bit more information, which makes for a good heading. We need to provide labels with units. Kinetic energy, here it's still measured in kilojoules. We haven't done that conversion yet. We haven't needed to do it yet. We're going to need to do that when we do some calculations. And displacement measured in meters. So those are the labels with the units for the axes. The mark for plotting is basically just for the accuracy of how well you plotted this graph. A line of best fit. The line of best fit, notice, doesn't go through the first point and the last point. It doesn't necessarily have to go through any particular point either. Here you see it does go through this point and it does go through this point, but that's not a requirement. Basically, it needs to be a line that is a best approximation of the trend of this data. And as a good approximation, you want to have as many points lying above the line of best fit as you do below the line of best fit. And then lastly, you had a mark awarded for scale. And that's for having a good scale for both your horizontal and your vertical axis. 7.3, you're asked to state the work energy theorem in words. Basically, it's about the net work done to an object being equal to the change in kinetic energy of that object. So it's quite important that you use the word net because it's the network, and it's about the change in kinetic energy. Both those aspects are quite important. In question 7.4, it's a very short question, but conceptually it's a little bit challenging. Let's look at it a bit carefully. You have a bucky starting from rest. That tells you that the initial kinetic energy and the initial velocity of the bucky are zero. We're asked to use the work energy theorem to derive this statement, that the kinetic energy of the bucky is simply equal to the net force acting on the bucky multiplied by the displacement undergone. We're further asked to assume that the net force acting on the bucky is in the same direction as the displacement. That makes sense in this particular scenario. So, starting off, here we have the net work done is equal to net force multiplied by displacement multiplied by cos theta. That's from the definition of work, and that's a formula straight off your formula sheet. Cos theta falls away because the force and the displacement are in the same direction, so theta is equal to 0 degrees, and cos of 0 is equal to 1. So we simply have that the net work done is net force multiplied by displacement. Now, net work is also equal to your change in kinetic energy. That we have from the work energy theorem. The change in kinetic energy is your final kinetic energy minus your initial kinetic energy. The initial kinetic energy we've said is 0 because the bucky starts from rest, in which case your change in kinetic energy in this instance is simply equal to the final kinetic energy, only in this instance because the bucky starts from rest. In which case, your net force multiplied by your displacement is equal to your final kinetic energy, which we have here in the last line, which is the line that we were asked to derive. Earlier in the question, we plotted a graph of kinetic energy against displacement. We plotted kinetic energy, EK, on the y-axis. We plotted displacement on the x-axis. And written in this particular form, I hope it's clear that your net force must be the gradient of a graph of kinetic energy versus displacement. So the gradient is your net force. This allows us in question 7.6 to use the graph to determine the average net force acting on the bucky. There are a couple of different ways to do this. The best thing to do is look at your line of best fit, calculate the gradient of the line of best fit using your usual expression, rise over run, or delta y over delta x. In this particular case, it's the change in your kinetic energy, delta EK is basically delta y, divided by the change in your displacement. So delta x is still delta x. This would be your gradient. Performing that calculation should give you something between 11,540 newtons and 12,960 newtons. You need to be very careful here to convert from kilojoules into joules, and you need that conversion factor of 1,000, so it's definitely of the order of 12,000 newtons or 12 kilonewtons. Very important to pay attention to the units here. In question 7.7, we are asked to determine the magnitude of the applied force of the engine of the truck. The only forces we don't really know are this applied force, so we're able to set up an equation that allows us to solve for it. The frictional force, we've been told, we've been given, it is 1,200 newtons. The net force we've just determined from question 7.6, on average about 12,000 newtons, in this particular case 12,195 newtons. The gravitational force will be counteracted by the normal force perpendicular to the slope, so the only component of gravity that adds to the net force is the x component, or your parallel component of gravity. So your net force is given by this expression over here. It is your applied force, it is friction acting against the truck, and it's the x component or the parallel component of gravity. Notice that we've written plus friction over here because we're treating F net as a vector sum, where the frictional force Ff is a negative quantity itself. The parallel component of gravity we need to split up and expand a little bit into mg sine alpha. Here alpha is the angle of incline given as 15 degrees. G is the acceleration due to gravity of 9.8, and 2,500 kilograms was the mass of the bucky. This negative sign here is because the gravitational component parallel to the slope is acting down the slope. This is negative here because your frictional force is also acting down the slope. So this is actually using a direction convention of up the slope being positive. In that case, your applied force must come out as positive as well, because that's the only force acting up the slope, and overall your net force must be positive as well, because the truck is moving up the slope and it's accelerating. Substituting values in and then rearranging allows you to solve for the applied force, roughly 19,700 newtons.